Hi, Dr. Ariel. I'm here today to discuss the undamped oscillations derived from Law of Mass Action paper by Alfred Lotka as part of my presentation. So what I'll be talking about includes the premise of the article, the types of oscillations that exist, as well as the products of the chemical reaction, which is really what this paper is about, and the cause of the reaction, as well as the period. So, in the premise of this paper is that Alfred Lotka suggests that chemical reactions can, in some certain circumstances, exhibit an oscillatory character. So, what that implies is that if you take the example of a pendulum, is that a chemical reaction can transit between different states in a constant fashion. So as you would see in a pendulum, it would move from point A to B to C and back from C, B, and A. So he tried to illustrate what that would look like using a series of mathematical derivations. So when you talk about oscillations, you're talking about two types of oscillations, the damped and undamped oscillation. So in a damped oscillation, the amplitude or the rate of the reaction decreases with time. So as you would see in a pendulum, as it transits between the different points, as time goes on, the pendulum itself decreases in its movement. So that is how that chemical reaction would look like. The rate of the reaction decreases until it comes to a point 0. So, but in an undamped oscillation, the rate or the amplitude of the oscillation, it does remain constant with time. And intuitively, this is hard to imagine, but Lotka was able to come up with a series of mathematical derivations and equations that show that the product of the chemical reaction, illustrated by x1 and x2, are a function of time. So to be able to start his derivation, Lotka made a couple of assumptions, one of which that the beginning substance known as S of O is in constant concentration. So, and that would usually be produced by having an excess of S of O or combining a saturated substance with an undissolved substance. So in the first instance, where you have an excess of S of O, the product will be homogeneous, while in the second instance, the product will be heterogeneous. So for the heterogeneous reaction, the chemical reactions that take place, they are slow compared to diffusion effects. So that was the two assumptions really that Lotka made. So in illustrating the what the products would look like, Lotka used this graph to show that the oscillations are really can be illustrated by closed curves. So this shows the period, the P2 here will show the period of the second reaction, which is which comes from the beginning substance. So S of O will produce a beginning substance, will produce substance S1 and substance S2. So S2, which is formed from S1, has its period P2, while S1 has a period P2, so P1. So they go in an anti-clockwise fashion, and P1 would usually make a greater excursion than P2. So this shows the positive quadrants of X1 and X2, which is of most interest for this discussion. And this equation, the differential equation that is seen here, is the equation of this graph. So to delve more or discuss more about the period of the oscillation is independent of the initial mass of the product, so the product quantity, which is x1 and x2. However, the amplitude defined by constants a1, b, a, b, a prime, and b prime, as seen in the paper, is dependent on the initial masses of the product quantities. So what does that imply? It means that when you have any two reactions with an undamped oscillatory character, what you will see is that when you start them off simultaneously, they will move at a similar pace, even if one waveform is faster than the other. So each of these would, as you would see for the period, this illustrates two different reactions. So you would see that the period P2 is moving in the same direction at the same pace, even though one has big greater waveform than the other. So an application of the undamped oscillation is or rhythmic phenomena as illustrated by undamped oscillations in biological systems is the heartbeats that you see in a human being, which also moves in an oscillatory manner. However, Lotka does not go into detail on how this would work in a human heart. So this concludes my presentation on undamped oscillations derived from law of mass action by Alfred Lotka. Thank you.